Hello and welcome back to another YouTube video, and in this video we're gonna solve a LeetCode problem, which is conversion of an integer number to an English word. This problem has one input, which is the number integer, which has a maximum value of 2 billion, and we want to convert it to English words. For example, 1 to 3, which is 123 and 12,345. Right, so I have made a conceptual view so we can have a better understanding of this problem. If you don't know how number works, or maybe you're just not good in English with numbers like me, there are a couple of videos you can watch and learn more about numbers. Alright, so what are numbers? So I have listed down the numbers from 1 to 99, so we can have like a visual relation between the numbers and its connection between each other. We have like 1, 2, 3, 4, 5, 9, 10, 15, 17, 18, 19, 20. Until then we have like unique values, like there is no duplicate. You can't see 1 or anything. It's just unique. From 1 to 20 there is uniqueness in those numbers. After 20 it gets more interesting. We have 21, which is made of 20 plus 1. Alright, 22, 20 plus 2. Alright, so 26, which is 20 and 6. 29, which is 20 and 9. And when we hit 30, it's just 30. And so on until 40, and 40 is the same relation as 50 and 60 and so on. Alright, sorry for that. So moving on, like 40 is same logic for 30 and 50 and 60 until 90, and 99 is the last 2 digits, which is using the numbers below 20. So that's it for the numbers from 1 to 100. So what makes number less than 20 kind of unique? From 1 to 20, they are used for numbers which are bigger than 20, like 25, which is 20 plus 5, like 36, it's 30 plus 6, like 77, and so on and so forth. So what happens in the numbers between 20 and 99? We have tens for each number, like 20, 30, 40. That's kind of unique, cool. It's a unique number, and you will be using it in more in bigger numbers like 100 and so on. But if it's not tens, like 21, 34, 55, anyway, it's just containing of, like 21 here, it contains 20, which is a tenth of 21, and it's remaining. So it's 21, and 34, its tenth is 30, and the remaining of 34 is 4, so it's 30 plus 4, it's 34, and that's it for the number between 20 and 99. So our unique numbers are this kind of one, which is 1 to 10 for 1 digit, and 11 to 19 for single digit, and for the tens, which is 20, 30, 40 until 90. And we have a special case, which is 0. This special case is just 0. You just say the number 0 if it's 0. If it's not for example, if it's 20, we just say 20. We ignore this 0 at all. So it's a special case. So for numbers bigger than 100, that's really interesting. So we start off by 100, which is simply 100. There is 2 0 besides this one. We just ignore the zeros, and we have 101, which is 1 at the left side, and there is the 2 digits, which is 0 and 1. So 0 and 1, which is less than 20, so it's kind of the unique numbers we're gonna use, which is 1. So we have like 101. Like this, we have 1 at the left, and there is 2 digits at the right, so we have, which 2 digits, 5 is less than 20, so it's 105. 12 is also less than 20, so its unique value 19 is the same. Once we start to want it 20, it's 20 is unique, it's 120. Right now it gets real. 121 here. How can we start analyzing this? We have the left side, which is 1, it's 100, and now we have the 2 digits beside 1, which is 21. How can we solve this? We have 21, the tens of 21 is 20 plus the remaining, which is 1, so 21. We have 128, the same logic applies. We have 100 here, we have 28, the tens of 28 is 20, and the remaining of 28 is 8, so it's 100 plus 20 plus 8. 146 is the same, 146, the tens of 46 is 40 plus the remaining, which is 6, so 146. It's the same for the remaining. Let's get to 200 to see another number instead of 100. 200 is the same, like 2 is on the left side and there is 2 digits on the right side, which are 0, so it's unique case. We ignore just 0, so it's just 200. 202, we have the 2 on the left side, there is 2 digits on the right side. 02 is smaller than 20, so basically you just add the unique number of 2, so it's 202. Let's get, for example, for 244. How can we solve this? 200 on the left side, so we say 200, and 44, which is the tens of 44 is 40, and we add the remaining, which is 4, so 244, until we hit 999. I'm sorry, and that's it, like 900 from left side, and there is 99, which is the tens of 99 is 90, and the remaining of 99 is 9, and we just add this kind of meaning. So how is the number bigger than 99? It just gets bigger and bigger. 1000, like 3 zeros at the right side of the 1. We can, what happen if we just add 1? So it becomes 1000, and there is 3 digits, and those 3 digits are less than 20, so basically we just use the unique number of 1, which is 1, so it's become 1000 plus 1. 1026. How can we solve it? We have like this one here, 1000, and there we have 3 digits. 26 is 2 digits, is greater than 20. We have the tens of 26 is 20 and plus 6, so basically it's 1000 plus 20 plus 6. 1969, that's really confusing number. Anyway, it's 1000 here. Right now there are 3 digits, which are 969. How can we do this? Like, we take the first number is 900, and we have the second 2 digits, which is 69. The tens of 69 is 60 plus 9, so we have 1969. I will skip this, and I will get probably at 63,000. And how can we see this? Like, we have 3 digits next to 63, so 63,000, and we have like 3 digits here. So how can we calculate this? We take 500, and there are 2 digits on it on the right side, so which are greater than 20. So the tens of 22 is 20, and the remaining of 22 is 2. So basically it's 500 plus 20 plus 2, and plus 63,000 that we have first calculated. Oops. Alright, so big number, 702,961. How can we calculate this? We have like, there are 3 digits here, and there are 3 digits right at the right side. So let's calculate the left side first. We have 7 here, so 700, and we have 2 digits here which are smaller than 20, so its unique value, we're gonna 702,000 because of the 3 numbers next to at the right side. Now we have another 3 digits, which is 961. How can we calculate it? We take the 9, and there are 2 digits next to it, so it's 900, and this 61, the greater than 20, so the tens of 61 is 60 plus 1, which is the remaining. Let's get bigger and become millions. So we have like 1 million here, this 1 million is just simple. There are so zeros, so we just ignore the zeros. Now, for example, if we have a couple of zeros but not all zeros, so we have like 1 million here, we have zeros here which we are gonna ignore. We have like 3 digits here. How can we calculate it? Like 300, 2 digits are available, so we're gonna take the tens of 21 because it's greater than 20, and which is 20 plus 1, so it's gonna 1,321,000. All right, so really big number is 13,241,673, which is great. How can we solve this? All right, so we have 13, which is just 2 digits, which is smaller than 20. So basically we're gonna, which is unique value, which we just say it as it is, 13 million. And we have another 3 digits, which is 241. How can we solve it? It's 200 there, and 41, we just get the tens of 41, which is 40, and 1 is the remaining of 41. So that's it. Right now we have 13,241,000, and there are 3 digits here, which make us say 1,000 after calculating this one. Alright, now there are the last 3 digits, which is 731, which we just calculated like the previous one. We 600 there, and the other 2 digits, which is 73 greater than 20, we take the tens of 73, which is 70, and add the remaining, which is 3. Alright, so this really big number, it's 9 digits, so we're gonna take the first 3 elements, which is 694, that's 600, and 94, which is greater than 20. We calculate the same way. We have 94, the tens of 94 is 90, we add the remaining, which is 4, and there is 6 digits, so basically it's 694 million, which is 694. 575 is the same calculation like before, and so on. Let's see a real example on how we can apply it for a billion. Alright, so this is the last element possible for integer, but if you want to scale it for quadrillion or quintillion or whatever you want, trillion, you can achieve it by applying the same algorithm we're gonna apply it here. So we have this great number and we want to solve it. So first of all, we're gonna take the left side at most, which is 273, and there is 9 digits at the right side, so we know it's a kind of billion. How can we solve this 3 digits, which is like the previous steps? We have 273, we need to have the 273, so we divide the whole number by 1 million, 1 billion, I mean, just to get the last 3 digits, which are 273. And once we have the last 3 digits, we can convert it to words by specifying the first number, which is 2, and there is 2 digits on the right side, so it's basically 200. And we have 73, the tens of 73 is 70, and 3 is the remaining of 73. So right now this 273 will be converted to 273 billions, which we calculated based on the division process we have made. So now we have finished the left side. Now we go to the next 3 digits, which is 694. 694 has 6 digits next to it, so basically it's a million. We can make sure by dividing it by 1 million to obtain the 694 digits. And how can we alright, conversion of 694, we have like 6 digits there, so we know it's a million. 694 converted like the same 3 digits we have converted it the previous slides. 694, we take the 600, and with the other 2 digits 94, the tens of 94 is 90, and we have the remaining of 94 is 4, according to the tens of 90. Alright, so it's gonna be 694 million because of 6 digits we have here, And now we're done with the million. Now let's get to another 3 digits. We have 575. How can we calculate it? It's the same way. It's 500, 700, 575, which is the second 2 digits. The tens of 75 is 70 plus 5. We just we add like 500 plus 70 plus 5,000 because there are 3 digits at right side. So now we have the last 3 digits remaining. It's 213. There are no more digits on it, so we're not gonna add any thousand to it. We're not gonna add millions. We're not gonna add anything. It's just the last number, which is 200. And there it's 13. 13 is smaller than 20, which is a unique value, so it's gonna be 213. So in order to make it this step, so first of all we calculated the billion by dividing it by 1 billion, which resulted in our 273, which we handled it like the 3 normal digit cases. Now we need the million. How can we find the million? How can the 3 digits needed for the million? We just take the remaining of the billion result, which is 273. Like we just want to ignore this 273, so we can use the remainder operator. So we're gonna take the full number and the remainder divided by modulate by 1 billion, which is resulting in the remaining of 273, which is the remaining of this. Now once we got the remaining, we're gonna divide it by million just to get this 694, 3 digits, so we can calculate how many numbers in million, which we have calculated 694, which is just this. Now we have calculated the million and we need now the thousand. How can we achieve the thousand? We're gonna take the remainder of the previous million, which is 694, 575, and 213. How can we do get the remaining of this million? We're just gonna divide it by million, and not divide. I'm sorry again. It's module. We're gonna modulate by million, and once we get our thousand number, we're gonna divide it by thousand, so we have the final the last 3 digit for 1,000, which is 575, and we calculate it using the same logic for any 3 digits, or 2 digits or 1 digit, so on, but we have used 3 digits a lot, which is 575,000. And now we are at the last number, which is 213. How can we achieve this? We take the previous 1,000 and we get the remainder of it, which is gonna be 213. 213, there is no division there, so it's just gonna be 213, since 13 is smaller than 20. And if we added our 273 billion plus 694 million and 575,000 and 213, once we add all that, we will achieve the final word for this number, English word. So that's it for our solution. This operation will run in time complexity of 1 and space complexity of 1 if you're going to use recursion, which I will be using since it takes memory stack. And that's it for our solution, and see you in the code. But be aware, if you're gonna do this algorithm for bigger number, for example like long or big integers, so you need to decide which data structure you're gonna use. See you at the code.